which is 100 pounds, 100 pounds of CO2 is contained in a 10 cubic feet tank. The safety limit of the tank is 1600 psi G. Use the compressibility chart to estimate the maximum permissible gas temperature. All right? So we have here 100 pounds of gas. What is that gas? CO2. And the volume of the tank is 10 cubic feet. It's given to us. So we have a tank that is 10 cubic feet. Now the safety limit, which is the pressure, maximum pressure, is, it can go is 1600 psi G. So what is the real pressure there? What's that? Plus atmospheric pressure. So the real pressure would be, this is equal to 1600 plus 14.7, that's equal to 1614.7 psi. A, absolute. Okay? Now, we know the pressure, we know the volume. Do we know the how much gas is in there?
Yes.
How much gas is in there? Yes, 100. So N is equal to number of moles, right? Equal to 100 pounds, which is the mass, 100 pounds, divided by 44 pounds in a pound mole, right? So this will be equal to, now, how many pound moles?
2.27.
So we have 2.27 pound moles of gas that is in there. So we know N now, we know, we're trying to figure out temperature, we know V, we know P. But this P being at high temperature, or P being high pressure, we cannot use simply PV equal to nRT, we need Z. So let's calculate Z here, okay? Let's calculate Z. How do we calculate Z? Reduced pressure and reduced temperature. So now reduced pressure equal to P over PC. What is P here? P is 1614.7, right? Divided by, what is the PC for, CO2? Google. Well, but you have the book, or I will give you the data. But right now, we need to get that, right? Do you have the book? See? You need to have the book or Google. One of the two. All right, let's go and see here. CO2, carbon dioxide. Carbon dioxide. Carbon dioxide. How much is that? 7.37 megapascals. All right, let me do here straight away atmospheres, which is 72.9 atmospheres from the book. 72.9 atmospheres. Okay, this is atmospheres. And so now we have to convert. This is PSI. This is atmospheres. So now 1 atmosphere equal to 14.7 psi, right? So what do we get here? 1.507. Wonderful. All right. So now, what is the TC here, or TR now? That's what we're trying to figure out. Right? Now we can calculate first VR. VR is reduced volume. VR equal to molar volume PC divided by RTC. Basically, it is V1 P1 equal to N1 T1 kind of correction here that we are doing. Okay, this is the standard volume, and this is the volume at a different temperature and pressure. So that's what we're trying to figure out. Molar volume at reduced temperature is equal to, the standard volume that is given is 10 feet cube, right? 10 feet cube. And we have PC. PC is equal to how much now? How much is that?
It's 1071.
No, we don't even need to go through this, but we might need. We're trying to calculate T there, right? Yes. Yeah. Let's do that. So PC is equal to what? 71.5. Divided by VR equal to,
Isn't the volume constant?
what's that? Volume is constant. Yes, volume is constant. I mean, we're trying to calculate going back to what would that volume be at a different condition. So the volume is standard volume that we have there, a cylinder. But what would that volume be? Now let's see here. R is what? R would be 10 point. Now we want it in feet cube atmospheres, pound moles, Rankine. We want it in 10.73 would be in PSIA. So we would use here, if we are using 79 atmospheres, not 10.73 but 0.732. 0.732. Okay, molar volume is equal to, actually this is not PC. Let's see here. Yeah, that's what it is, NRTC here, NRTC. So what would happen here is the pressure that we have is actually the P, which is 72.9. This is not PC, folks. This should be P actually. That's the initial condition. Initial condition, or the condition at which we know the volume, which is occupied by this. So which is 10 cubic feet we have 72.9 atmospheres inside pressure, right? And then we have N equal to 0.732, which is what we have. And then we also have here temperature, at what temperature it is holding, which would be your TC at critical temperature. That's what we will figure out. Instead of standard condition, we will figure out at TC. TC would be for this carbon dioxide. TC would be carbon dioxide, TC, 304.2, right? Yeah, 304.2 Kelvin. So 304.2 Kelvin. 304.2 Kelvin. And then this is the volume, 10 cubic feet is the volume that is occupied by how much gas now? How much we are putting in there? 2.27 moles, right? Are you guys following? Okay. So now what are we calculating here? Yes, Ricky.
Why is it not PC? Because we are using V over PC, and I thought like PC means NRPC.
Yeah, yes. What is the pressure that we have there? The atmosphere, the pressure in yes. PC is the critical pressure, right? Yes, PC is critical pressure. So let's use that. Yeah, you're right. We could use that. I'm sorry. Here you can use PC. Yes, PC. So basically, at critical pressure and at critical temperature, what would be the molar volume? Which is volume occupied by 1 mole. So at this pressure, which is 72.9 atmospheres, the volume occupied is 10 cubic feet, and this is N, this is R, this is the number of moles, 2.27, and this would be your TC. So what will be the volume here? Volume occupied by 1 mole. I've got numbers, so let's do the calculation here. Any numbers?
1.45.
10 cubic feet times 72.9 divided by 0.732 divided by 304.2 divided by 2.27 equal to 1 point. How much are we getting? 1.44. Okay. 1.44. Oh, okay. There's one wrinkle here too. I think is it. What are we getting here? We are using here. What is the temperature in Kelvin? And this 0.732 is what? 0.732 should be Rankine, right? So there is a correction there that we have to apply to this value too, whatever we are getting here. So now this is, what we have here is Kelvin, and this constant is for Rankine. So we need to actually change that a little bit. 1 degree Kelvin equal to 1.8 Rankine. So if we do this, what will happen? Now, divide this number that we have, 1.44, by 1.8. 0.8. So that will be our volume here. 0.8 is the volume, which is basically the VR, which is reduced volume, which is at volume occupied at critical conditions. critical pressure, critical temperature, what is the volume per mole. Now, if we go back now and look at our charts, which is our goal is to get actually the Z, right? If we go back and look at our chart here, since our pressure, reduced pressure, or volume, reduced pressure we already calculated, which is 1.5 up there, right? 1.5 up there, reduced pressure PR. So we should be using here the chart that is on the left side, which goes from 0 to 10 atmospheres, which is on the page 210. Page 210. All right, which is 5, 4, 3. Okay, by looking at this, you can get here, there is VR, ideal, dotted lines there, right? You see that? And also you have on reduced pressure at the bottom. So reduced pressure on x-axis, we have to look for 1.5, all right? And then reduced volume is 0.8. So up there, 0.8. 0.8 and 1.5 will give us roughly a factor of 0.85. 0.85 roughly. So Z equal to compressibility factor, Z is equal to 1.5 and 0.8. Slightly less than 0.85, but 0.85. 0.85, let's say we get that number. Okay, now once we have the Z, now we are trying to calculate here. Now we are trying to calculate the temperature. Yes, the temperature is equal to here, PV, or PV equal to nRT. So temperature equal to PV divided by ZnR. Right? ZnR. Are you guys with me? PV equal to, or T equal to PV divided by ZnR. So now, in this case, P is equal to what? 1614.7, right? And then V equal to 10. This is PSI divided by Z is now we have 0.85. N equal to 2.27 moles, and R equal to, what's that? Yeah, we could use 10.73 because everything is in PSI. Yes, 10.73. So what will be our value here now? 780 Rankine. Wonderful. So what will that be in terms of Fahrenheit? Minus 460. That will be 320 Fahrenheit. So the maximum it can go to is the temperature it can go to the cylinder is 320 degrees Fahrenheit.